Welcome back, chemists. Today we're going to talk about how we use various analytical techniques to identify what molecules are. We've been talking about how to separate them into different components. We talked a little bit about how to use physical properties and chemical tests to identify certain substances. But now we're going to move on to some more modern techniques that chemists have been using in the last 50 years to identify what substances are. So here on the screen I have an example of what's called a supporting information section for a publication. And anytime a chemist makes a molecule, if it's brand new and never been made before, they have to say what they did to make it, and they also have to provide data that shows it is what they claim it is. So here's a schematic that shows a typical reaction, just abbreviated for a chemical transformation. But molecules in the real world never look like the pictures we use to abbreviate them. They look like white powders or various liquids and things like that. So how do I know that something like this has this structure? It's a very involved task. And we can use things like physical properties that we've talked about, like melting point, to start to pinpoint what that molecule is. And there's a variety of other techniques that chemists use to identify them. The one we're going to look at in this lesson is called mass spectrometry. And mass spectrometry uses the molecular mass of a substance. It actually determines the molar mass of something. And then that helps us figure out what the molecular formula might be. And that really starts to indicate what its structure might look like. So on your notes, I have a schematic of what a mass spectrometer looks like. They fit on an average desktop and are usually hooked up to some type of computer readout. And they work by ionizing samples with an electron gun. Remember, ionization simply means you lose an electron from that substance, so it turns a molecule into a charged molecule. And once the molecule is charged, it can be affected by things like a magnetic field. So a sample is injected, a molecule is ionized, and then affected by a magnetic field. And as they pass through a magnetic field, different types of ions, different parts of the molecule, will be deflected differently. So lighter ions deflect more than heavier ions. And we can see that in the picture. These narrower bands show the least massive ions, and the thicker bands are apparently the more massive ones. It's also crucial to know that in addition to ionizing a molecule, the conditions of the mass spectrometry will fragment molecules. They'll literally break apart and lose some of the covalent bonds, and we'll see that in the spectra. So just to introduce the concept, I'm going to play a little matching game where let's pretend we have 4 different organic compounds and we're given the 4 mass spectra that correspond to those, and we just have to figure out which one goes with which. Well, mass spectrometry shows us the molar mass of that compound, as well as some other pieces of information. So before we look at the spectra, let's look at each compound and figure out what the molar mass of those compounds is. Notice that each one in these pictures is made of mostly the same 4 elements. The first one is an example of what's called an amide. That's an organic functional group that refers to this part of the molecule. You don't need to know that yet. We're going to get to that later in the year, but I'm just going to use it to label this molecule. The second one is an example of what's called an ester. The third one is a nitrile, and the last one is what's called a ketone. And the 4 elements that are primarily present in these compounds are carbon, hydrogen, oxygen, and nitrogen. And if I go to a periodic table, I know the atomic masses of those elements. Carbon is roughly 12, hydrogen is roughly 1, oxygen 16, and nitrogen 14. So I'm going to jot those down. Carbon is 12, hydrogen's 1, oxygen 16, and nitrogen 14. And now I'm going to figure out what the molecular mass is for each of these 4 compounds. Well, the amide has 5 carbons, 11 hydrogens if you count them up, 1 nitrogen, and 1 oxygen. And if I add up all of those atomic masses, I get 5 times 12 for all the carbons, 11 times 1 for all the hydrogens, 14 times 1 for the nitrogens, and 16 times 1 for the oxygen. That gives me 101 grams per mole for a molar mass of the amide. This is just to the nearest whole number. Obviously, we could do this to more precision, but for the purposes of this, the nearest whole number is perfectly fine. So I want you to hit pause, figure out what the molecular formula is for the remaining 3 molecules, and then calculate what the molar mass should be for each of those as well. Okay, if you've got your molecular formulas and molar masses, the ester has 6 carbons, 12 hydrogens, and 2 oxygens, giving us a molecular mass of 116 grams per mole. The nitrile has 7 carbons, 5 hydrogens, and 1 nitrogen, giving me 103 grams per mole. And lastly, the ketone is 3 carbons, 6 fluorines, and 1 oxygen, and no hydrogens, which is rather unique. And also fluorine, I don't have jotted down, so let's go back to our periodic table. Fluorine weighs 19, so if I add up 3 carbons, 6 times 19, and 1 more oxygen, I get 166 grams per mole. So how do we figure out which mass spectrum goes with which molecular formula? Well, if I zoom in on the first one and talk about the things I see, on the x-axis you have what's called the mass to charge ratio. That's effectively the molar mass of the pieces that have made its way to the detector in the mass spectrum. The y-axis is the relative intensity. How much of each of those ions do I see relative to one another? The most important peak to look at for molecules is the one all the way to the right. That's the parent peak. It's the highest number, and it's usually going to correspond to the molar mass of that compound. So this is easy. 116, that corresponds to the ester, so this must be the ester. But what's going on with these other peaks? Well, if you remember earlier in your notes, we said that the conditions of the mass spectrum are such that you could actually break covalent bonds. Some of the bonds in this ester can be broken literally under the conditions of the reaction, of the experiment. And that's what gives us these what are called fragmented peaks. It's not crucial to identify all of them. In fact, for this exercise, we don't even have to identify any of them, but it does give us insight into what the molecule looks like. For example, this 101 right here is exactly 15 less than 116, and that would be a loss of a CH3 group from the molecule. The 57 here happens to be the tallest peak. That's called the base peak in any spectrum, and that's just the one with the highest relative intensity. There's nothing really special about it other than that. And if I had to identify this, that would be what I got if I broke the molecule to the left of the carbon in the middle, giving me 4 carbons and 9 hydrogens. That would add up to 57. So you can see how the different fragments in combination with the molecular ion peak can really start to piece together what the structure looks like. Even if I didn't know what the structure looks like, this is very useful information. So I want you to hit pause again and just identify the remaining 3 spectra to correspond which molecule they go with. Okay, if I look at the next one in the upper right of your notes, I notice this peak at 103. That corresponds to the nitrile. You might have said, wait a minute, what's going on with this peak down here at 104? Well, exactly 1 more than 103 must mean we gained a hydrogen somewhere. And under the conditions of the experiment, you can sometimes pick up a hydrogen just from acidic media, and it will do an acid-base reaction. You can even lose an H under the same conditions. So you sometimes see plus or minus 1 from the parent peak. The 76 would be a loss of 27, and a little arithmetic shows me that that's an H plus a C plus an N, so the rest of the molecule could be showing up as this fragment at 76, but again, it's the 103 that's the most important. Moving on to the next one in the lower left, the parent peak of 101 corresponds to the amide, and if I had to identify the 59, well, that would be a loss of 42, because 101 minus 42 gives me 59, and that would be if I had 3 carbons and 6 hydrogens sort of chopped off of the amide, leaving me this remaining fragment of 59. And by process of elimination, or just using the same numbers, 166 corresponds to the ketone, and I can see other fragments easily identified by losing fluorine atoms. The first one at 147 is exactly 166 minus 19, so that's what I would see if I lost 1 fluorine from this molecule somewhere. The 97 could be if I lost 3 fluorines and a carbon, so one of the CF3 groups on either side could be cut off. In fact, 69 shows up as its own peak right here, which would be a CF3 itself. So that's how mass spectrometry is useful for identifying molecules. It gives us the molar mass of the molecule, gives us the masses of fragments, and starts to identify what the structure could be. Lastly, let's look at what we can see with elements in mass spectrometry. So here in problem 27, I have 3 elements and their respective mass spectra. And what I need to do is identify what these peaks are and what element each one is. And you might be saying, well, if this is an individual element, if I go back to my periodic table, shouldn't I just see something close to 1 number? But remember, atomic masses on periodic tables are decimals. And those are decimals because of isotopes. So mass spectra actually shows you the different masses that correspond to the different isotopes. And that's why the numbers can often be so close to each other. So instead of looking at the biggest numbers, I'm actually going to start with the smallest numbers in this case for the elements. In this case, the 35 and the 37. And if I look at my periodic table again, that sends me to the area where chlorine is located. And indeed, this is the spectrum of chlorine. So chlorine is massed between 35 and 37, but in nature, all the isotopes are either 35 or 37. And that's why we see something in between them on the periodic table. We can also use this mass spectrum to identify what the different abundances of those isotopes are. Here on the relative intensity scale, the chlorine isotopes that are 35 look like they hit at about 82 on the y-axis, whereas the 37 isotopes hit around 27. So 82 out of the total is chlorine 35, and 27 out of the total is chlorine 37. So how do I get the percent abundances? Well, I take that ratio of 82 divided by the total. That gives me the percentage of chlorine 35. That turns into 75%. And then the remainder, or the other one, 27 divided by the total, gives me the percentage of chlorine 37, and that's how you get 25% of chlorine 37. So 3/4 of chlorine atoms exist as chlorine 35 isotopes, and 25% of chlorine atoms exist as chlorine 37 isotopes. And how do you get the atomic mass, the weighted average? Well, 75% times chlorine 35 plus 25% times chlorine 37 gives you 35.5 grams per mole, and that's why periodic tables have chlorine's average atomic mass of around 35.5. This particular one is obviously to a higher precision than the information we're getting from this spectrum. So what's going on with the peaks over here to the right? Why do we have these bigger numbers at 70, 72, and 74? Well, remember, chlorine is diatomic. So these are chlorine molecules, where I have 2 chlorine atoms coming together, where each of them is chlorine 35. Here I have 1 of each at 35 and 37. And lastly, 1 chlorine 37 and 1 chlorine 37 coming together to make 74. So there's a lot of information in this spectrum of pure chlorine, because in nature chlorine exists as so many different isotopes. Well, just 2 of them, but because it's 2 isotopes and it's diatomic, we see a variety of peaks in the spectrum. So I want you to hit pause again and look at the remaining 2 mass spectra of 2 other elements, considering what isotopes they may be and where they are in the periodic table, and then try to identify what elements they are and what relative abundances there are, just like we did in the previous example. Okay, so if I look at this spectrum, again I'm going to look at the lower numbers, and I see peaks hovering around 80, 79, and 81. If I look at my periodic table, bromine hovers right around 80, so this is probably a spectrum of bromine, and we can prove it. It's easy to look at these 2 peaks here. They're clearly in a 50-50 ratio, so the atomic mass is much easier obtained in this example. It's 50% 79 plus 50% 81, and that gives you a weighted average of 80 grams per mole, which is almost exactly what bromine is on a periodic table. Keep in mind, none of the bromine atoms weighs 80. Half of them weigh 79, and half of them weigh 81, and that's why we see this in the mass spectrum. But on average, an average bromine atom would be 80, even though none of them actually do. And once again, off to the right, bromine is diatomic. So these larger peaks correspond to 2 bromine atoms coming together, the 279 isotopes, 1 of each, and the 281 isotopes coming together to make the largest peak. So lastly, I have a simple spectrum here with something at 10, something at 11, and that's it. Going back to our periodic table, this must be boron. So here's a mass spectrum of elemental boron. Boron is not diatomic, so this is just the different elements, the different isotopes of elemental boron as single atoms. And we can figure out what the relative abundance of each isotope is from this. The y-axis isn't even marked off, but if I make it go up to 10, the lower boron 10 shows up at about 2.2, and the higher one shows up all the way at the top at about 10. So what's the percentage of each isotope? Well, the percentage of boron 11, the bigger one, would be how much of it there is, 10 divided by the total, 10 plus 2.2. That gives me 82% boron 11. And then the remainder, 2.2 divided by the total, gives me the percentage of boron 10. And that's 18% boron 10. So most of the time it's boron 11, and then the rest of the time it's boron 10 according to this. And then the relative weighted atomic mass is 82% boron 11 plus 18% boron 10, and that gives you 10.8 grams per mole, which is almost exactly what we see on the periodic table. So just to summarize, mass spectrometry gives us lots of information. Primarily, we can use it to get molar masses for compounds. We can get atomic masses for elements, specifically weighted average atomic masses, because elements exist in different isotopes, and that lets us also give isotopic abundances. So lots of useful information thanks to mass spectrometry as an analytical technique.